Hi, today we are going to continue our work with simplifying trigonometric expressions, and today we're going to focus on the Pythagorean identities. So you probably recognize from the name that we might be talking about the Pythagorean theorem, and that's actually where these identities come from. So if you recall from our work with basic trig, when we have a right triangle that's sitting on the unit circle, our radius is equal to 1. And our distance horizontally along the x-axis is our cosine value. And our distance vertically, so along the y-axis, is our sine value. Whoa. That's a little harder to write sideways like that. In any case, just like in the regular old Pythagorean theorem, if I square the legs of my right triangle and add them together, I'll get the square of my hypotenuse. So we would have something along the lines of sine squared plus cosine squared is equal to the hypotenuse squared. And if we're sitting on the unit circle, then that hypotenuse will be 1, and 1 squared is of course 1. And this is where our very first of the Pythagorean identities comes from. Now, if I divide everything here by cosine, so I would get everything here divided by cosine, and specifically cosine squared. Then what I would get is sine squared divided by cosine squared, which is tangent squared. Cosine squared divided by cosine squared is 1, and 1 divided by cosine squared is secant squared. Those are based on the reciprocal trig identities. And you could probably tell that that's this one right here. So how do we get this third of the Pythagorean identities? Well, pretty simple. Instead of dividing everything by cosine squared, I'm going to divide everything by sine squared. And so if I divide every single term by sine squared, here we go, dividing by sine squared, then sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. And 1 divided by sine squared is cosecant squared. And as you can probably see, that is where we get this third of the Pythagorean identities from. So if taking our original Pythagorean identity and dividing everything by sine squared gives us our third piece that involves cotangent and cosecant. Now, these are not the only way that you can write your Pythagorean identities. We can use the inverse operations and we can isolate a variable, or in this case, a trig value that's squared. What I mean by that is I can actually subtract cosine from one side of the equal sign to the other, and this would leave me with sine squared of x is equal to 1 minus cosine squared. Or if I wanted to, I could isolate my cosine squared, so get cosine squared alone. And so moving the sine squared to the other side using the opposite operation, I would get cosine squared is equal to 1 minus sine squared. So anytime that I'm working on a problem and I see a cosine squared just sitting there, I know that I could go in and I could do a substitution using this Pythagorean identity. So instead of writing cosine squared, I could write 1 minus sine squared. and they're equivalent. What's probably more usual is that I might see something that says 1 minus cosine squared. And I could say, oh, well, I know what 1 minus cosine squared is. It's actually sine squared, and I could use that as a substitution. But wait, there's more. I can actually also try the same thing with my with my 1 plus tangent squared plus secant squared formula. So with this one, I could isolate the number 1 if I wanted to. And that would mean I'd have to move tangent squared to the other side. So I would get secant squared minus tangent squared. So if I see a 1, I could replace it with secant squared minus tangent squared. Or if I saw something that said secant squared minus tangent squared, I could write a 1 instead. This one's already solved for secant squared. What if I wanted to solve it for tangent squared? Well, that wouldn't be very hard. If I start with the original, in order to get tangent squared alone, I would simply have to subtract this 1 and move it to the other side. So that would give us secant squared minus 1. But let's not leave our cotangent squared, cosecant squared Pythagorean identity out. No, this one is already solved for cosecant squared. If I wanted to, I could instead solve it for cotangent. I would just have to subtract this 1 over to the other side. This would leave me with cotangent squared is equal to cosecant squared minus 1. And I could also solve it for 1. And if I wanted to do that, I would simply have to subtract cotangent squared to the other side, leaving me with cosecant, I keep on doing that, cosecant squared minus cotangent squared. And thus again, we know another Pythagorean identity. So starting from the one piece of information we knew from the Pythagorean theorem, sine squared plus cosine squared is equal to 1, I was actually able to write 8 more Pythagorean identities. Pretty cool, huh? And for several of these, I have the fact that 1 is equal to something. So 1 could be a whole lot of things. Sine squared plus cosine squared, 1 could be secant squared minus tangent squared, or 1 could even be cosecant squared minus cotangent squared. These are all substitutions that I could make if I wanted to simplify a trig expression that uses a Pythagorean identity. Again, here's some of my favorite strategies. It's nice to put things in terms of sine and cosine. Sometimes you need to factor. Occasionally it's good to combine fractions, and make sure you multiply your numerator and denominator by the same factor. Now, one thing that I have noticed that happens when we start to introduce the Pythagorean identities is because there's so many of them, plus all the other identities that you were given previously, it starts to become a question of which one do I use and how do I know when to use it. And that's kind of the beauty of the game. You are really just trying to get to a simpler expression. So choose substitutions that are going to make what you have written down simpler and that are going to lead you to having less terms or a singular term, maybe no more squares, maybe not having such a big mix of different trig ratios, all in the same expression. And there are lots of different pathways to take. You don't necessarily have to stick with the same one every time that your friend might have, for example. So let's check out this problem. I see that it's set up nicely for the distributive property. When I see a minus sign in front of a set of parentheses, this is like telling me it's a perfect time to use the distributive property. Now, I could try and use a substitution for tangent or cotangent beforehand, but I think I'm just going to go ahead and try distributing this minus sign. So I get secant squared plus cosecant squared minus tangent squared. Oops, that x got crazy. Minus cotangent squared. And I say this every time, but do not forget to distribute that minus sign to the second term inside your parentheses. You don't want to get it wrong because of a negative. So at this point now, I'm thinking maybe there's going to be a good Pythagorean identity that I could use. So let's go back to our Pythagorean identities page and see what we've got. So back on this page, I saw that with a negative tangent, a positive secant squared will make 1. So secant squared minus tangent squared is equal to 1. Well, here's our secant squared, and here is our minus tangent squared. Together, we know that those equal 1, right? So I've got 1 plus cosecant squared minus cotangent squared. Where did my secant squared and negative tangent squared go? I replaced them with a positive 1. That's the substitution of the Pythagorean identity. So next, let's look at what we have here. I've got cosecant squared and a negative cotangent squared. So with my Pythagorean identities, a cosecant squared and a cotangent squared, that sounds like this third set, and it was the cotangent squared that was negative. So it looks like cosecant squared and negative cotangent squared is equal to 1. Cosecant squared and a negative cotangent squared is equal to 1. That's one of our Pythagorean identities. So I can rewrite this as 1 plus 1. I'm just substituting in 1 for cosecant squared minus cotangent squared. And altogether, this is equal to 2. See how nice having those identities can be? It can make it a lot simpler. Yes, I know I didn't go ahead and rewrite everything as sines and cosines because I did have these kind of handy identities that I could use for my substitutions. Let's keep going. Here's another one. Another strategy is to try and factor and then simplify. So looking at this, my numerator doesn't have much for me to factor, so I'm just going to kind of keep that the same. 1 minus sine theta. And then down below here, I see this sign of negative theta. This is one of our even and odd identities. I happen to know that the sign of negative theta is the same as negative sine theta. And this is from our prior lesson. So this is my odd identity, since sine is an odd function. So I'm going to rewrite my denominator using this particular identity. So I have the cotangent of theta, and then since the sign of negative theta is really negative sine theta, this plus sign is going to turn into a minus sign, and I have sine of theta times cotangent theta. Looks like I need to extend my division bar. Whoop, whoop. There we go. So now I'm going to do the factoring in the denominator. My numerator stays 1 minus the sine of theta. However, in my denominator, both terms have a cotangent, so I'm going to factor out the cotangent theta. Cotangent times 1 gives me cotangent minus sine. And cotangent times sine gives me sine cotangent. Now looking at how it's written here, it looks like I have a 1 minus sign on top and a 1 minus sign on the bottom. Any number divided by itself is equal to 1. So this actually can simplify down to 1 divided by the cotangent of theta. Now 1 divided by the cotangent of theta is one of our reciprocal identities. The reciprocal of cotangent is tangent. So I can take it out of this form and I could write it tangent. Because as you know from our reciprocal identities, the tangent of theta is equal to 1 divided by the cotangent of theta. So I just used that substitution. See, this one didn't even need to use the Pythagorean identities. Let's continue. So for example number 3, we're asked to simplify by getting a common denominator and then to combine it into one fraction. So when there are fractions, one strategy is to focus on the reciprocal functions first and then simplify. That could get rid of the fractions. And so let's try that. So I've got secant beta divided by sine beta is equal to cosecant beta divided by secant beta. So I'm really interested in what's going on with this second fraction. So I'm going to write it or rewrite it using my reciprocal trig. So I know that cosecant is really 1 divided by sine. Don't forget to write your argument. In this case, it's beta. Now, secant is really 1 divided by cosine. So this has actually created for us a complex fraction, a fraction divided by a fraction. And if you're in my class, you know I love these. So I'm going to multiply by the reciprocal. 1 times the cosine of beta, which is the cosine of beta, divided by the sine of beta times 1, which is the sine of beta. So this whole fraction is actually equal to the cosine of beta divided by the sine of beta. So what we have here is, and I'm going to write a little equal sign so we can see that this is actually equivalent. We have the secant of beta divided by the sine of beta minus the cosine of beta divided by the sine of beta. Okay, well, I can see here that my denominators are the same, so I can combine the numerators. So I get the secant of beta minus the cosine of beta, all divided by the sine of beta. And gosh, this doesn't seem very much simpler. I mean, we are definitely in one fraction instead of two fractions. But we could also maybe change our secant to a cosine. And in order to subtract those fractions, I'd have to get a common denominator. So this denominator needs to be a cosine. Ooh. Let me rewrite as neatly as I can what I have now. In the numerator, I have two fractions that are being subtracted. 1 over cosine minus, this is now a cosine squared over cosine. So I'll have 1 minus cosine squared divided by cosine. And then don't forget the denominator, just been hanging around this whole time, is sine. But check this out, you guys. I hope you're going to like this. 1 minus cosine squared. Did anybody notice that? Just hanging around, looking innocent. But it's not that innocent. It's really sine squared. So we're going to go ahead and replace that with our Pythagorean identity. So 1 minus cosine squared is really sine squared. So I have sine squared divided by cosine, all divided by sine. Now you might be thinking this almost looks like a complex fraction, and you'd be right. And we can make it one by simply dividing our sine by 1, because sine of b is the same as sine of b divided by 1, right? So let us do that complex fraction. We're just going to multiply by the reciprocal. I'm going to get sine squared times 1, which is sine squared, divided by cosine times sine, and then this, we're almost there. We can simplify. Any number divided by itself is 1. So I have 2 cosines up here and we have 2 sines up here and 1 sine down here. One of them will cancel out on the top and on the bottom. This leaves me with the result of sine divided by cosine, which is equal to tangent. Our final answer. What did you think? Pretty cool, huh? Now let's try another one. Let's try and simplify this one. So this is kind of interesting. We've got a fraction being subtracted from the whole number 1. I see a sine squared. I'm going to do something a little crazy. I'm going to rewrite this so I have 1 minus. Instead of writing sine squared, I'm going to use one of my Pythagorean identities. So I'm going to write 1 minus cosine squared. So you might think this looks like it's getting more complicated, not getting simpler. Okay. There is a method to my madness. One of the things I love about the Pythagorean identities is that they are a difference of 2 squares. One is a perfect square, and cosine squared is a difference is another perfect square. With the minus sign in between, it's a difference. So that thing is totally factorable. It's factorable as 1 plus cosine times 1 minus cosine. Now, why did I think of doing this? It was because of that 1 plus cosine in the denominator. I was just thinking, man, I really wish that wasn't there. And I know that 1 plus cosine and 1 times cosine is 1 minus cosine squared. So I figured, why not try and use the Pythagorean identity? Because now any number divided by itself is equal to 1. And all I have here is 1 minus the quantity 1 minus cosine theta. Now this is set up for the distributive property, which I personally believe is the most important property in math. It happens everywhere. We need to distribute this minus sign to both terms inside of our parentheses, and we got 1 minus 1 plus cosine. Because a negative times 1 is negative 1, and a negative times negative cosine is positive cosine. I know you know that 1 plus 1 is 0, so after simplifying, this brings us to our final answer, cosine. And that's what I have for you guys today. I hope that you are intrigued by these Pythagorean identities. They're just a few more that you can use in your arsenal to simplify these trig expressions. And I'm looking forward to talking to you next time. Bye-bye.